So what we left off with on Friday was this idea that you can represent organic molecules in many different ways. We've seen things like wedge dash depictions. We've seen now the Fischer depiction, in which we've gone backwards. We've stripped out much of the information and assumed that certain axes, whether they be horizontal or vertical, are pointing in set directions. So every time in a Fischer depiction, the horizontal axes there are pointing towards you. They are pointing out. They have to be. That is the definition. And this becomes very useful in biochemistry because you have a huge amount of stereochemical information that you have to pass along to the person reading this, and these become valuable. So you need to be able to... What, are we not texting anybody, are we? Put it away before I break it. We have to recognize that the horizontals are coming out towards you and the verticals are going away into the board. That is the way we do these. And you'll see very quickly that you can use these to describe the same thing as a wedge dash depiction, but they're much faster to write. They are much quicker to draw. Now, I like this stuff. I think it's very important that you get your head around this, especially if you're a biologist, especially if you're an engineer of any type, because you have to worry about these principles in the future, such as polymers that have set stereochemistry, organic materials like proteins, which are all stereochemical types of molecules. So we need to be able to do this from the wedge dash depiction in that direction, and then go from a Fischer depiction to the wedge dash. And what it is an exercise in can you do it? It's an exercise in manipulating things in your head which are flat on a piece of paper, but really in reality are 3D. You can use the models. Again, you can use the models on the exam coming up on the 18th, I think it is, and be good at this. So life is about to get more complex because it has to. We're heading towards your subjects. What I wanted to look at quickly here was the basic definition. There's what a Fischer depiction defines. The horizontal axis here, axis in this case, is going to be one chiral carbon. Now, as we start drawing these things, we don't draw a horizontal axis for every carbon. If it isn't chiral, we don't need to, because that's not a chiral center. We're only doing these horizontal things for the chiral centers. So the vertical lines into the plane, the horizontal lines out of the plane. And then we can start to use these things. And I think they become useful because you can see symmetry or lack of symmetry much easier in these molecules than you can in a wedge dash depiction. If we look at this on the left, if R1 is not the same as R2, is there any symmetry in that molecule? No. So the top chiral center will be not necessarily the enantiomer of the bottom one. And we can certainly quickly draw the enantiomer of that molecule by just drawing the mirror plane, drawing the mirror image across that mirror plane. And what we tried to do on Friday was suggest that these two are not superimposable, because what you have to do to superimpose them is turn this thing up on its end like that. So R2 ends up on top of R1. They don't match. And it still fits that very simple criterion that we started off, especially in recitation with the molecular models. Two of the things will match on a chiral center, but two of them won't. Okay, that's the idea of asymmetry again. So then we can very quickly run up a series. We can talk about the different isomers here. This guy over here is not the enantiomer of this one over here. I think it's much easier to see in a Fischer depiction than it is for a wedge dash depiction. So that's good. And we can see now that this does not match this across the mirror plane, even though this does. And we've used that term diastereomer to explain that relationship. Diastereomers, hopefully you've picked up now, are basically stereoisomers that are not enantiomers. It's as simple as that. So we think about how to apply this, and this is what you need to be practicing as soon as you can. Certainly to get the homework done on Wednesday and the quiz done on Wednesday, because we're going to be into 6 today, is to turn these things into Fischer depictions and also go in the opposite direction. So we should by now be very quick at this. How do you do this? What's number 1 on that carbon? Bromine. What's number 4? Hydrogen. Is the hydrogen in the correct direction or the wrong direction? Correct direction. So once I work out 1, 2, 3 clockwise, and the hydrogen is already orientated in the right place, the right way, that's the R stereocenter, yes? And if you can get that done quickly, within seconds, that really helps, because we're going to start using this stuff. Bromine here, number 1, this will be number 2, that will be number 3. The hydrogen's in the right place already, so that's also the R stereocenter. So when we can build off of those things, we can build a series. We said about 2 to the n. The maximum number of isomers you'll get will be 2 to the n, depending upon how many stereocenters you have. And sometimes there are fewer. The fewer being the meso idea, where you get some symmetry. And I argue it's not so easy to see the symmetry in these things. Yeah, it's not particularly easy to see the symmetry. But if you turn these things into Fischer depictions, we start to see symmetry. You can see here very clearly that if I slice this thing in half, the top matches the bottom. And you think of this in terms of optical rotation. If the molecule is chiral, it will have alpha D of some number that isn't 0. But if you put these two stereocenters, which are the opposite of each other, it's like having a mirror plane. It's like having the R and the S in the same molecule. The light will cancel out. And so what did we say alpha D was for this? 0, right? They cancel out and alpha D is 0. Now alpha D, we talked about what it was, we defined what it was. It's now going to be used. It will be a big clue to help you work out what's happening in a chemical reaction. How do you do this? Well, we've spent time in office hours. We've been doing this sort of thing quite quickly to try and show how these things are related. If you want to come to office hours, do so. We'll do it in recitation as well. But you can do this. It's not too difficult. And once you get it organized, it's quite useful. So we need to recognize that in the wedge dash depiction, maybe one of your axes is in the correct direction, but the other one isn't. And you have to change one. You have to rotate around that central carbon-carbon bond to get this in the right order. And then now we have the Fischer depiction, which certainly shows the symmetry. So they are useful. In terms of going in the opposite direction, we'll worry about that. We'll worry about how to practice that. There are plenty of things out there. You've got the course pack with Chapter 5 material. You've got the online homework. You've got the textbook. There's an awful lot of stuff out there to practice. Please do so. And do it soon, because we're about to get swamped. Okay, Fischer depictions, very useful, very powerful, important stuff. In terms of going in the opposite direction, well, that's just practice. I want you to do both. I want you to go from there to here and also to there. Be comfortable with that idea. So to finish off, you know, it's all about exams, right? It's all about conquering this stuff and make sure we can do it. This next exam will have some nomenclature. It will have some of this R&S stuff. It will have something about relationships between molecules, and it will have mechanism. The bulk of it will be mechanism from now on. So if we look at this, what's the simplest thing you can do? You can look at those things, and the question is asking you, how are they related? Are they enantiomers? Are they the same thing? Or are they diastereomers? If you can see this, great. You're probably a lot further ahead than I was when I took this class first time, a long time ago. I just couldn't see this in space. I struggled with the 3D idea. And what I was taught to do was work out R&S. If you work out R&S and they are the same on both molecules, they are the same molecule. If you work out R&S and you get a different one, then maybe it's an enantiomer or a diastereomer. So if you're quick at doing R&S, you can work out that this is, what is that? RS. That's R. And what about this one here? R, right? They are both the R configuration. Now, when we go to the Fischer depiction, it's maybe not so easy, but you've got to remember, what's the problem with the hydrogen on that axis? It's in the wrong direction, right? It's in the wrong direction. So whatever we look at, I'm seeing clockwise, maybe you see counterclockwise. You're supposed to be looking from the opposite direction. So here's 1, here's 2, there's 3. That looks like clockwise. But what should it be? It's actually S, isn't it? And we said R over here. So now we have a test. Even if you don't see how to manipulate these things in space, you have a very simple test to be able to work out the relationship. So down here at the bottom, I have this, and I have this, and I have this, and that's counterclockwise as it looks. But what's the problem with that? It's the wrong direction, and that is R. Now, if this means nothing to you, it has to very quickly. This is, again, one of these principles that you'll be using again and again. And, you know, it's trying to, like trying to build a house without knowing how to use a hammer. Yeah, it doesn't work. So make sure we're happy with it. So the idea there being that they are RRSR. And what's the relationship now? They are diastereomers. And also be very careful. There's a lot of information on these pictures right now. Right? We've built up quite complex ideas so far. You've got to make sure they have the same connectivity, because if they don't have the same connectivity and the atoms aren't in the same order, they're not even related. So here we have carbon, 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 as you do in the backbone. That checks out. On this carbon we have a hydroxyl, yes we do, and on this carbon we have a bromine, yes we do. They are certainly related as some type of stereoisomer or identical. And the very simplest way to do it is to work out the R and the S and then match them. So on this type of example, because this is all about speed and it's all about being good at it quickly, does anybody see the relationship straight off? Does anybody see what manipulation you have to do to see if they're the same thing or enantiomers? Yeah, you have to turn one over, right? You turn one over in the plane of the board, you see that this goes here and this goes here. So what do you think the relationship is quickly? They're the same. Now, if you don't see it, you can work out the asymmetry. You can work out the R and the S. That sounded expensive. They don't bounce, do they? Well, I'm happy for you. They both work out to be the S and the S, so therefore they are the same thing. Yes, they're identical. Very quick thing to pick up and very, very useful. Now at the bottom, I argue these are the most complicated ones, most difficult ones to do, because you're being asked to look at a Newman depiction against a wedge dash depiction. These are all mixing together the different ideas and the different sort of representations we've drawn, and now using them and being quick at identifying them. Well, you can work out R and S. Or, if you're good at this, you can imagine, you know, this is looking from the side, and I have to look from here to be able to look from the same direction for that molecule. And if I do that, maybe my hydroxyl is pointing out towards me, and my fluorine is pointing out towards me. And if I turn this thing around in space, I'll find that they're mirror images. Do you think you can superimpose them? Do you think there's any symmetry in this system? No. So if they're non-superimposable mirror images, what should they be? Enantiomers. So if you can see that straight off, great, that's how it works. If you can't, Get the models out, practice these things, work out the R and the S, and then see the relationship. Yep, this is absolutely not trivial. I can say that a million times and hopefully it will sink in. Questions? You are the quietest class of Americans I've ever dealt with. Maybe you're all Canadian. I don't know. Okay, there's a question here to worry about. We've talked about cis and trans in the cyclohexane systems. We said that most molecules look like one and not the other in terms of their orientations. And you can see here that this does look like the mirror image of that. But the issue here is obvious, right? They are equilibrating. You can have the chair flip, and you're going to see an average of the system. So you're not going to see a set, rigid system like you would for the ones that we've been looking at. You're going to see, in this case, some mobility and some flexibility. So these are said to be not enantiomeric on a cyclohexane like that, but the same thing because of the interconversion. You can go from one to the other, and you see an average of the two. So that's not a chiral system. So I'm finishing up. I have a little story to tell you, and then I'm into 6 very quickly. You should have picked up through your reading this idea that enantiomers have the same physical properties. You think about left-handed and right-handed. They should pack together the same, maybe in a crystal. They should have the same boiling point because they have the same intermolecular forces in either the left hand or the right hand. You know, they're essentially the same thing apart from their relationship through a mirror plane. So how do you separate these things? If you're building a drug, some compound that is one enantiomer, and you have to separate off the other enantiomer, how do you do it? And this comes back to this thalidomide story, where not separating them was a disaster. It was sold as RS mixture. Well, how do you get rid of the bad one? You have to have some purification technique to be able to do so. And this is more of an engineering idea, but it's done on huge scale in the pharmaceutical industry, and it's another reason why pharmaceuticals are so expensive. If you have to get rid of some junk that is a problem, it's going to cost you money. So what we do here in this schematic, and I have a real example on the next slide just to show you how it's done, is we take our mixture of enantiomers. Now, to put context in here, from nature, you typically get one enantiomer, not the other. In the lab, when you synthesize things, you typically get both. Now, if you get 50-50, you have to get rid of 50% of your mixture. It's a waste. What people are doing these days is trying to make just one enantiomer. Now, nature does it perfectly. You get one enantiomer because things have evolved to give you just that one answer. In the lab, we're at 99.5. Okay? We're getting very good at this, but we're not perfect yet. You get 99.5 of one enantiomer that you want, for reasons we'll see later. But what happens to that 0.5? If that 0.5 is a problem pharmacologically, you have to get rid of it. You have to purify it away. But if they have the same melting point, and if they have the same boiling point, have you done distillation yet? You haven't done distillation in the lab. You'll be doing it soon, when you can separate liquids by boiling them away. If they have the same boiling point, you cannot separate them by that technique. Have you done TLC? No. Have you done anything? You've done some bits and pieces, right? We have many separation techniques that won't work here because they have the same properties. So what we need to do is this, and it's very clever, but it's very expensive. We need to temporarily react these things together, these enantiomers, with some pure material that is just R, but not S. It's just one isomer and not the other. So where do we get that from? Nature. Some compound from nature that has just been, it's been biosynthesized and it's evolved to just be the one enantiomer, the one isomer. You go get it in large scale. And then you do some chemical reaction. And the example on my next slide is something as simple as an acid-base reaction. And you make a mixture. And that mixture now is a mixture of diastereomers. Because if I start out with RS here, and I'm just using, let's say, R here, I'm getting RR, and I'm getting RS. And they're not enantiomers anymore, they are diastereomers. Now, diastereomers differ by directions in space, and they're not enantiomers, so they do have different physical properties. If you have different properties, you can separate them. So we can do recrystallization. You have done that, right? Nobody can do it properly, but you have done it. You have to be very careful with recrystallization. So you can recrystallize things. One isomer might be more soluble in a solvent than the other. One crystallizes, you filter it off like you did, and you have a purified compound. And the other isomer is hopefully down here in the filtrate. That's very expensive on large scale, but that's how it's done. Well, we don't want these mixtures of diastereomers. We want enantiomers. So we have to have a chemical reaction to go back to our original compounds. And that could be something as simple as an acid-base reaction in the reverse sense to split those up. And what we've done through a fairly clever method here is to separate what look like inseparable compounds, turn them into diastereomers, separate them through physical methods that you have seen or will see soon, and then get your pure compound back. So this works. And the example from the book is as simple as this: a simple acid-base reaction. So this is a mixture of two compounds. It might be some derivative in a pharmaceutical synthesis, and you have to get it pure. You want the R maybe, you don't want the S. You need to get rid of it, right, to purify the right stuff. So what you do is you take this material. This is basic. Why is it basic? What's missing from this and this compound that tell you it's basic? What's missing from anything in there? What do I need to be a base? A lone pair. Where's the lone pair in this molecule? Nitrogen, right? So there's my lone pair, there's my base. Those things are amines, they are basic. There'll be a big chapter on that later. And then we mix it with this stuff. This is a natural compound, and it's one pure isomer. Well, how do you know it's acidic? Carboxylic acid. The word acid is a clue, right? Carboxylic acid. What's the pK of the carboxylic acid? About 5. So all I'm going to do here is a very simple acid-base transfer where that base goes after that proton and takes it off. And that will give me on the other side salts. Now salts typically are solids. And you've now got diastereomeric solids because you chose here both enantiomers mixing with only one enantiomer of this stuff. So you're getting a differentiation now. This material is not the enantiomer of that material. This has a wedge here and a wedge here. This has a wedge here and a dash here. And they're salts, so they're intimately combined, right? One matches the other, and you're going to be able to separate them. So the difference here is the stereochemistry at that carbon. The stereochemistry at this carbon is the same, therefore they are diastereomers. Therefore you can separate them by crystallization, and then we have pure material. But I don't want those compounds. I want my enantiomers back. So once you've got this separated, how do you get rid of that proton and take it back over there? What do you need to add? A base. It's as simple as that, right? It's usually the simple answer, a base. So you put some base in there, you take off that proton from the nitrogen, and you get your purified compound back. You need to know this for these silly standardized tests that you might have to take in the future, and it's also an indication for those who are interested in pharmacy or medicine why pharmaceuticals can be outrageously expensive, because we have to do this type of thing, especially when we're doing synthetic type compounds. So keep an eye on that story. It will become more useful in the near future when you've done those techniques yourself in the lab. So my last couple of slides in this chapter, in fact my last slide, this is what you should be up with by now, at the very latest by Wednesday, to do the homework and to do the quiz. I know some of you aren't doing the homeworks and the quizzes because you've given up, that's fine. But if you are hoping to do well in this class, you need to do those homework assignments. They're straightforward points, and they also force you to learn the stuff now instead of cramming it before the next exam, because that's fatal. What we've done so far, we've said that the universe opens up because molecules can be chiral. We can have chiral centers in which we have asymmetry. And to do that, we must have 4 different atoms or groups attached at sp3 carbon. So when you're practicing, don't be telling me that an sp2 carbon is chiral. It isn't. It's sp3 carbon. That's all you're dealing with. We had this idea of definitions. Enantiomers were non-superimposable mirror images, and if they weren't enantiomers, as the compounds got more complicated and you put several stereocenters in there, you're looking at diastereomers. Those relationships must be in there somewhere. Sometimes you don't get 2 to the n, you get fewer, and that's based on this idea of meso. And what do you have to have meso? What's the basic requirement for meso? Symmetry, a plane of symmetry. You must have that in there for it to be meso. And then finally, keep this in mind as we work into the more complex ideas soon. If you have n stereocenters, you can get 2 to the n stereoisomers. Anybody want to say anything? Because this is where it all starts to change. Is anybody nervous? Is anybody excited? Joe, you're excited. Good man. This is it. I mean, if you want to be in college, this is what it's about. I'm done with chapter 5. Goodbye, chapter 5. I'm going to start chapter 6. When we come to choose textbooks, which we did several years ago and picked this one, the reason we picked it largely was because the fellow who wrote it had written a handbook for organic chemistry, which dealt with organic chemistry as a language. And that's the philosophy that myself and Dr. Jackson have had for years. You teach this as if it were a language. Repetition helps. If you're speaking, if you're trying to learn something like Italian, and you're speaking to yourself in the mirror, and you're saying certain things, you're probably insulting somebody's grandmother. You think you're asking to buy a loaf of bread, and you're probably insulting their grandmother, because you're saying it wrong. All right? So this is like a language in organic chemistry. You've got to have the basics down to be able to put the reactions together. We've only done one chemical reaction so far, acid-base reactions. They are useful because they get you thinking about how things happen, It's not just on paper, it's actually physical dynamic processes in a flask, in a cell, in a person, where things hit each other and there's a reaction to that. Okay? The compounds do something to react to that influence. And what we've done in the first 5 weeks, because this is the beginning of the 6th in this class, is build up these ideas, many of which were from general chemistry. So hopefully at least you've cemented those ideas and you're comfortable with them. The idea of shape, the idea of VSEPR, valence shell electron pair repulsion theory. And electrons don't like each other, so we get these shapes. We get tetrahedral, we get trigonal planar, we get linear. Those are the fundamental building blocks now to be able to do organic chemistry and to be able to do reactions. Physical properties, this idea of intermolecular forces, boiling points, whether something's a liquid or a solid, is now going to be used to make chemical reactions work. Electronegativity and resonance. You must have resonance organized now so that we can start to use this to explain things. Acids and bases were the first example of this. And if there's one thing that's going to haunt you from now on, it's these things, reaction arrows. They're going to get very complex. There are going to be multi-step reaction processes which have 10, 15, 20 steps. And you've got to get these arrows correct. You can memorize it. I think that's painful. Or you can learn it from the ground up and make it logical and make it make sense. That's much more easy to learn and it's much more fun. Right, Haldeman? It's a lot of fun if you learn it properly. So in this case, we'll need to start worrying about what these can tell us. And we'll have to worry about, again, things like equilibria, which are often based on molecule stability. You want to go to the more stable molecule. It's as simple as that. In some instances, you've got equal stability on both sides. So you get an equilibrium constant of about 1. That means you've got all these different things in solution. If your equilibrium constant is huge, you've only got one set of things. Maybe you've only got the products. That's key now because we don't have any of the starter materials left and we've gone to a certain place. We did start talking about carbon. We started talking about alkanes and we started talking about their shapes, and we talked about cis and trans in the cyclohexanes and all that stuff. And the fact that they're always moving. You can't freeze these molecules out. They're always moving, so they're always changing their shape. And we can see here now conformation was really important, whether something was cis or trans made a difference in terms of their stability, and that was all down to molecule energetics. We're going to spend a lot of time in chapter 6 talking about that idea. What constitutes a stable molecule? What constitutes a weak bond or a strong bond? So that when we heat things up, what goes first? What breaks first? Then the last thing we did to get started here, the last sort of rule we needed to learn to get going into the chemistry, was this idea of configuration. Now, something you should pick up from this is that conformation is not the same as configuration. Okay? Configuration is your identity, right? Whether it's Michaela, whether it's me, we're different. That's our identity. But standing up, sitting down, that's a conformation within the same person. So with those ideas in mind, here we go. We are going to do a very heavy, detailed analysis of why compounds react. Why? Because we have to worry about polymer chemistry for the engineers, and we have to worry about biochemistry for everybody else. How do biological systems interact? Why do they interact? What's the benefit? And it's all rational. What pathways are possible? There are many. But they are defined into set chapters. We have 27 chapters we deal with in this class. We're in chapter 6 now. Every family of functional group that we have seen in a very basic way will have its own chapter because it has unique chemistry. But if we take this carefully and we deal with it in a mature way and do it day by day, it isn't overwhelming. That's why 55% of my class will get through 2 semesters. Okay, but it starts here. The success starts here. So what we need to worry about is things like energy. What constitutes more stable, less stable? Obviously things like electronegativity will play a role. Resonance will play a role in deciding where we want to go. What's better, the left or the right-hand side? So with that in mind, welcome to mechanisms. There's no going back from here. Your lives are about to change. Well, a mechanism is simply an explanation in steps of how your stuff that you put in your flask turned into your products. And you have done this on a very basic level in the freshman lab. You took acid and base and you mixed them together and you made observations. And you saw pH change maybe through an indicator. And maybe the flask got hot. And that flask getting warm tells you that it's exothermic. Tells you that maybe the products are more stable than the starter materials. A very simple physical thing, a very simple physical change. Well, what wasn't really hammered on at that level, and is now, and is from now on, is this idea of what exactly is happening. If I take a solid from a flask or a solid from a bottle and I put it into my reaction flask and I put some liquid in there and I mix them all up and I get something different, how did it happen? You can memorize what you get. There's a certain amount of memorization required here, but it's the fundamental understanding of how the two things spoke to each other, communicated, and went to the products. That's what mechanism is all about. And in chapter 6, again, the reason I like this book is that we take our time to define what a mechanism is. Instead of just diving into mechanisms as we used to, we just define now what is a mechanism, what are the possibilities, and what is the language that has to be understood to be able to do this. We'll see two types of basic process. All right? We'll see a situation in which we use the double-headed arrows. And that double-headed arrow right there, as you'll see very quickly, is telling you that 2 electrons are involved. We've done this with the acids and bases. So in a very simple process, we might see something like an ionization process, in which X and Y break apart, and we can produce ions when we dissolve things up, for example, in a solution. If you had to tell me in that situation which is more electronegative, do you think it's X or Y? Why? Why? Should be more electronegative, right? It's more electronegative because it likes taking the charge, it likes taking the electrons with it, so that's why it became negative, and that's why this lost out. In many of our reactions to happen very soon here, X plus will be a carbon. You've seen that in some of the homework. We've seen a 3-valent carbon with a positive charge. It's a 6-electron system, so therefore it's unstable. It wants to react with something else to become stable. And that Y minus, as long as it's good at breaking off, as long as it's a decent conjugate base, that will happen. So we'll get this ionization process. And the vast majority of what we will do in the 2 semesters involves that type of breaking. So we're getting a chemical reaction. We're getting a splitting apart of this molecule into 2 pieces. Those pieces might be stable, and they might not be. They might go someplace else. And all of a sudden what we've got is the first step in a mechanism. So that arrow here, this reaction arrow, is telling you that something changed. So be very careful. Those reaction arrows on the horizontal, the vertical, that's telling you there's a chemical change. This arrow here is a little device that we use to show how electrons are being pushed around, to show how the electrons are the glue holding the molecule together or to reattach the molecule. That's what they mean. Now, a little bit of what we do this term and a little bit of next term is this, in which we split the bond in an equal way. The top is called heterolytic because one atom gets both electrons. The one at the bottom is homolytic because both end up the same, and we end up with each atom getting 1 electron. So do you think this is likely to happen if Y is a lot more electronegative than X? No. So give me some atoms that are fairly close to electronegativity. C and H. Yeah, this will happen a lot with C and H in the future. And we have a marvelous chapter, chapter 10, based just on that, radical reactions of carbon. Now, this all used to be thrown into the same chapter. You got the double-headed arrows, and then 10 minutes later we were using single-headed arrows, and it was a mess. The people got lost. So we do a lot of this to start off with, and we do some of this later on towards the end of the term. By the end of that term, we've been through 2 exams. The people who are left are the ones who can do this, or the ones who want to do this, and they're taking it seriously. And we can lead into that stuff. Okay? 2 different types of arrows to use, double-headed, single-headed, depending upon what the context is. So you go back and you ask that question, why do things react? Why is chemistry such a big subject? Well, number one, look at the playing field. If you look at the number of atoms on that periodic table, it's large. The alphabet in this is very, very large. You think about the English language, it's with, what is it, 23 letters? And how many words you can put together with that? How many letters? 26. I don't do English. It has 26 letters, whereas we've got 100 and odd on that periodic table. We have a much bigger alphabet to make much bigger, many words. So it all comes back to this. Why do things react? Well, to become more stable, right? To become more stable. Why are we all here? To become more stable, to get decent jobs, to get good careers, to be happy, to be more stable. It's a very sort of fundamental driving force. And we go back to this picture in which we dealt with H2. You can see a lot of repeat here, lots of bringing together of ideas that you've seen. If you're not happy with this, you need to be. In this instance, we're suggesting that hydrogen 1s and hydrogen 1s on their own aren't stable because they've got that spare electron. And they're not of the configuration of a noble gas. They want to be. So what they do here is they connect. We might use this arrow and this arrow, single-headed, to couple those 2 pieces together and to give me a hydrogen molecule. So down here, we have H2, hydrogen gas, simply by putting those 2 things together. And what was the driving force? I've not used that term much, but I will from now on. Driving force. What is the driving force? Why should it want to do this? It becomes more stable. Down here is much better than it was to start off with. Why not go up here? It's too unstable. So we're starting to use this language about stable, unstable, reactive, unreactive, things like that, based on a very simple idea that you've seen at least twice now, my class and the freshman classes. So when atoms bond together like this to make the molecules, they want to become more stable. That's why they fulfill the octet rule. Well, we're going to do a lot of the opposite. Yes, we're going to have atoms come together and bond, but we're also going to have atoms sort of uncouple and give us different species. And I'm going to say on the right-hand side that these things are reactive. And in fact, they're often not isolated. They're often formed in a chemical reaction as intermediates along a pathway, and then they go someplace else. So this is maybe the first time we have seen the phrase reactive intermediate. They are both reactive intermediates. We'll see radicals are absolutely essential radical intermediates. We'll see carbocations down here, positive charges, reactive intermediates. They are formed. We can prove that they are formed, but they're not going to be stable. They're going to go someplace else later. So this slide is trying to show you that it's going to require something for this to make this work. If this bond is very weak, maybe you just have to look at it and it breaks apart. Maybe you have to put it in the sunlight and it breaks apart. Maybe you have to heat it up and it breaks apart. So you think about how you put energy into a system in the lab, most of the time it's heating it up. But you can also shine light on these things and introduce energy that way. So this is going to take energy to get from one side to the other. We'll have to decide how to design experiments. Do I need to warm this thing up or do I need to cool it down? We've already done some of this when we did the acid-base chemistry. If you have an acid-base reaction that is highly exothermic, what do? Do you run it cold or do you run it hot? Do you want to take the energy out? Do you want to put more energy into a reaction that's already highly exothermic? You want to cool it down, right? Simple lab procedure. Do you want to cool it down so you absorb that energy and you don't start a fire? In this case, we'll have to put some energy in because of the fact that that's a bond in its own right and it's stable, and we're going to disrupt this by breaking it apart. Now I'm going to use symbols. I'm going to use delta for heat, and later on I'm going to use h nu, E equals h nu from physics, for light energy. Those are both sources of energy that might allow this to happen. But we have to put some effort in to make this thing go, because you're breaking a stable bond. Down at the bottom, this isn't so obvious because we're asking this thing to break apart in a different way. We're asking this thing to break apart into ions. So what we'll do here is maybe we'll introduce something to speed this up. Maybe this is a slow process going from stable to unstable. What sort of device or thing can you add to a system to speed up a reaction? A catalyst. And we know what a catalyst is, and we'll see it in great detail in the future. So maybe this requires a catalyst. And an awful lot of what you'll have to worry about in this first... What is that? Catalyst. There we are. An awful lot of what you'll have to worry about in this first semester is the catalyst. When do you use it? What does it do? Do I get it back? The mechanisms require that recycling of that catalyst. So we are now going to think about how to manipulate organic systems by either heating things up, shining light on them, adding a catalyst, and seeing what comes about, what changes. This is a very gentle introduction to this. I'll be done with 6 on Friday, I would guess, and then 7 next week is, whoa. Well, this is logical. If you heat a molecule up that has different bonds within that molecule, which one do you think will break first? The weakest. The weakest. That's all there is to this. There's no mystery here. The weakest bond will break first. And that's when we get to chapter 10 and we do the radical halogenations. It's usually the weak halogen bond that breaks. How do you know this? Well, these have been devised over the years. You've done some of this in the past. You've done Hess's law, right? Where you measure the bonds on the left and you measure the bonds on the right. You see what the difference is, and that's going to tell you something about whether that reaction is viable or not. You don't need to learn all of these things. But you do need to have some handle on what is a strong bond and what is a weak bond. If we stay awake, you'll thank me later. You will, when you're successful. You really will. So, what's a strong bond? Well, it depends what money you use. Well, it doesn't really. All right. In the old money, where I was taught, it was 104 kilocalories per mole. But in your, in American money, it's 435 kilojoules per mole. One's about 4 times as big as the other. It doesn't really matter. But 100 kilocalories per mole is a strong bond. Yeah, for a single bond, that's very strong. So these CH bonds are strong. It's a good idea to familiarize with these numbers. Not memorize them, but get the idea of what constitutes strong and what constitutes weak. So in this case, the CH bonds, the HH bonds, they're typically very strong. And then we head down to some of the halogen bonds. HBr is getting weaker. HI is getting weaker. And we could argue this has a lot to do with size. HI, right, the I is huge, the H is small, they're incompatible in terms of their overlap. Maybe that constitutes to be a weaker bond. CC bonds are quite strong. They're quite difficult to break. We'll have to do some work to do that. We've got all sorts of ideas here for halogens. Again, look at that. Methyl iodide, CH bond, or the CI bond, is about half the strength of a carbon-carbon bond. Why is that? Probably the incompatibility. The fact that C is small and H is huge, they just don't communicate very well. And quite often, if we make an iodide, we have to stick it in the fridge, and we have to put aluminium foil around it. You'll take a brown bottle, put the stuff into it, and put aluminium foil around it. What's that trying to do? If you're trying to take, it's a brown bottle, dark, and then you're putting foil around it, what are you trying to avoid? Sunlight. Yeah, because the sunlight will pop that bond. So these are real things to worry about. And we'll spend a lot of time in the later chapters talking about these different bond energies, but I would like you to know that straight off, halogen bonds are weak. That's a good thing to look at. And bonds up here between C and H and C and C are strong. So when we ask that question, which goes first, we have some idea of what does, a little bit about why it does. So don't memorize that table, just be familiar with the general terms right there. We've seen these before, I hope. Have we seen reaction profiles before? Okay, you're going to see many of them. You're going to love these things. Michaela. The weaker the bond. Yeah. Okay. So we're going to move into descriptions of chemical reactions using these graphs. And this sounds a bit of a contradiction, but to me, as a chemist, this is a mechanism. These are used for mechanism the same way the arrows are used for mechanism. So we'll put these things side by side, and we'll trace these things. And particularly in recitation, when we hammer this, we'll talk about how the curly arrows are used to show bonds forming and breaking, and how those things that are formed along that reaction profile are found here and here and here. So we'll match the two, and we'll be able to talk very quickly about relative stabilities of things along a reaction profile based on the principles that we've seen so far. There is nothing difficult about this unless you make it difficult yourself by not putting the time in. It's as simple as that. You get out what you put in. So in this example on the left, we have, in this case, the change in enthalpy in the system. And we have a reaction happening. It's just generic. We're starting here by mixing something in a bottle or a flask. And then we get a change. And that change involves going to products. So the definition here of a product is what you get out. And you can isolate, you can filter, you can distill. That's the product. And in this case, the products are more stable than what you start with. So should this be favorable or not? It should be a favorable process. This makes all the sense because we're going to get products that are more stable and better than where we started. And we always get this guy. Okay? What is this? Activation barrier. We'll explain activation barrier in a bit more detail. If you have to take PChem, you'll learn it in a great deal amount of detail. But we'll learn it enough to be able to use it and handle it. What's at the top of that barrier? Does anybody know this? Transition state, right? Transition means change. It's something that's occurring as the system is changing. It's not a real molecule that we can see. We can't actually measure transition states, but we have a good idea of what they look like. It's basically as the system is changing, it's the top of that energy barrier. It's the highest energy point. So we have what's called an exothermic process, and on the right we have the opposite, endothermic process. Exactly. And you should be able to look at this thing and tell me right now, what is K for this process? Greater than 1, less than 1? Less than 1, right? Starter materials are preferred. But if these barriers are surmountable, we could argue that this is an equilibrium. Yeah? As long as those barriers aren't too high, you can go backwards and forwards. And you can set up equilibrium. Maybe in this case, the left-hand side is favored, so the equilibrium arrow would look like that. But you do have a simple system now to explain what we've done. And you can apply these to all the chemical reactions we did with acids and bases. If you were to mix, just to see how you know this already, if you were to mix NaNH2 plus CH3OH as an acid-base reaction, and you get on the right-hand side CH3ONA and NH3, which of those two graphs applies? The one on the left. So those who don't see it, what am I asking? I'm asking you to solve that problem. I'm asking you to work out pKa's, because guess what? pKa's are measures of this difference. It's a thermodynamic piece of data. So what's the pK of this guy here? 16. What's the pK over here? 38. Which side is favored? The right-hand side, exothermic. So now we're going to apply these graphs to these equations, and many more like them, which are more complicated, and use the data we can get from those graphs and the experiments we can do to work out what's happened in the process. So this isn't trivial at all. We can use from the ground up. A lot of these energies have been measured. So we can use, if you remember Hess's law, but see what's on the left, see what's on the right in terms of bond energies, bond strengths, and then see which is more favored. So in this system, which we'll do in chapter 10 later on, the question is, if you mix this stuff, this alkane with this halogen, am I going to get these products, and is it viable? And you can go to that table and pick up the different bond energies, and you'll find out that yes, it turns out now that the stuff on the right is more stable than the stuff on the left. John, over here. Just because you don't like this stuff doesn't mean she doesn't. I want you both to pass, I really do. Because I get sick of seeing you after year. If you look at this now, the right-hand side is completely favored, right? Because the bond strengths are much better than on the left. That's how we play this game. And those are things you have done in the past. You can measure those things quite nicely. Enthalpy is to do with energy, but entropy is also to do with energy. It's an expression of energy. How does a molecule dissipate its energy? And entropy is fairly easy to understand. Okay? You've got definitions out there. You've probably learned this definition in the past. You'll see now that it plays a large role in whether organic reactions are viable or not, how viable it might be. So what do we understand as entropy? What sort of definitions do we have out there? Say again? Unusable. I don't know if it's unusable. Entropy? Actually, that's a good way of thinking about it. It is the tendency to disorder, is a good way. Yeah, it's the opposite of cleaning up. Yeah, tidying your room is the opposite of entropy, right? Because your room's probably a mess, like your kitchen or whatever. It's doing the dishes in the opposite sense. In a chemical organic sense, it is the expression of energy. And the more molecules you have, the more ways you have to express. And the more rotations you have, the more methods you have of expressing that. So molecules that are breaking into two, you now have two pieces that are bouncing around. You had one piece that was bouncing around, now you have two pieces that are bouncing around. So when you get more pieces formed in this chemical reaction, that's favorable. Entropically, that's favorable. Enthalpically, it might not be because you have to break a bond. But entropically, it is, right? More ways to bounce around. Now, this is also common when you do things like this, when you take a cycle. Why is a cycle ordered more so than an acycle? Because it's rigid. All that stuff we did in chapter 4, where the cycles only have so many ways of expressing themselves, but unlike an acycle, when you break it apart, this thing can do this, right? You've got rotations everywhere. So this one has more freedom, more degrees of freedom, you might say. And so this one is favored. Down at the bottom, if you do reactions that you'll see in the second term, and you bring two pieces together like this, two pieces were expressing themselves quite nicely, and you brought them together to make one. Is that favorable or unfavorable? Unfavorable, right? You took away some of its methods of expressing itself. Down at the bottom, you'll see this in the next chapter. We have a plus charge here and a water molecule coming in, and we make this guy. Is that good or bad entropically? 2 to 1. Bad, right? You've got more order now. And you'll also see systems like this enthalpically are favored also, because you've got a positive charge with 6 electrons going to a system in which you have 8 electrons. So we're going to see a balance. And where does that balance come about? You've seen this before. It comes about here. We are not going to do calculations. We are going to look at this simply as a method for coming up with an overall answer without necessarily any numbers to show that a system is favored or not favored. And this is my last slide for the day, and then you're going to do some studying. So delta G, the overall Gibbs free energy in a system, is a balance between enthalpy and entropy. Yeah? And we're going to find that you want to have your delta H negative, because overall delta G has to be negative for this process to work. So if delta H is negative, great. If you go to something more stable, great. If your reaction process is exothermic, great. But it's also a balance between this. You're adding this entropic factor. And that entropic factor has this variant here. This variable here. What is T? Temperature. So how can you affect entropy? What can you do to a system if you have a flask in the lab? What can you do to change that delta S in its quantity? You can heat things up, you can cool things down. Right? So we'll find very quickly in the next couple of chapters very nice systems in which if you want to go to one direction and you want to go to a certain type of material, you might cool it down. And if you want to go to the other material, you might warm it up. Okay? Because we can play around with that entropy factor simply by changing the temperature. What you need to know by Wednesday, because I'm about to go into some very, very complicated stuff, is basically what that equation is trying to tell you and some of those principles we just talked about. So if you come into class on Wednesday and you don't know what entropy is, don't bother. All right, see you in recitation.